Hello all. This is the third lecture regarding the topic refraction through plane surfaces. In last two lectures we talked about Snell's law and refractive index or optical density, and we also talked about how when light refracts its wavelength and speed changes, but frequency remains same. Now today we are going to talk about some application of refraction, or we'll try to understand some phenomena with refraction, and these are the some phenomena. So we'll talk about real and apparent depth, bending of stick, then refraction through a glass slab, and then we'll talk about how we can experimentally verify Snell's law and two laws of refraction, and how one thick plane mirror can form multiple images. Now moving on to the first topic, real and apparent depth. So if you have seen, suppose, swimming pool filled with water, then you will see that it looks that its base or the bottom of the swimming pool has been shifted a bit up, and same is applied to anything. Suppose if you have a glass of water, and suppose you put this water over anything, then you will find the surface will appear to be shifted up. Okay, so that we are going to understand it. So real and apparent depth. So suppose we have a container and there is a coin here at the bottom of the container. Let us say this is object and this is water. So this is the real depth. We are writing it h. So h is real depth, and suppose we take two rays. This ray is going straight because angle of incidence is 0, so angle of refraction is 0. Now if we take ray, one more ray, and now this is the angle of incidence on this surface, and it will bend away from the normal. And if you extend this reflected ray, let us say it meets here. Now you know that image is generally formed by two rays. So one ray is this, one ray is this. So this is our image. Now this height we are writing h prime. H prime is called apparent depth. Now even these two rays looks very far apart, but actually in real way they are very close. So both are intercepted by your eyes. Okay, so both two rays will be intercepted by your eyes. This is the angle of refraction, and you can also see that this will be the angle of incidence, alternate interior angle. So you can see, if you look from the top, this object will appear to be raised up. Okay, now this shift we are writing it by y. This is called apparent shift. So y, which is h minus h prime, this is called apparent shift. Okay, now using Snell's law and some trigonometric identity, we can derive a relation between h and h prime. Right now we are not going to do it. So it turns out that h prime comes out to be h by refractive index of, let us say, this is some denser medium, refractive index of medium. I am writing with respect to air. Okay, m stands for medium. So h prime comes out to be this. Now to understand this, suppose you have a paperweight. So its glass refractive index is 1.5. So this is glass. So refractive index of glass with respect to air is 1.5. So H prime will be H by NGA. Okay, so you can see that H prime is 1.5 times less than H. Okay, now this shift can be also written as y equal to H minus H prime is this. I am writing H by N. N is the refractive index of second medium with respect to first. Refractive index of the first medium from which light is going. So let me write 1, 2. Refractive index of. Now y becomes 1 minus 1 by N. So you can see this apparent shift depends on some parameters. One is how much is the medium is extended, H. So you can say depth or the thickness in which the second this denser medium is present. So it is H. So y depends on H. You can see that. Then it also depends on N. Now we all know that the refractive index of, so this, suppose we take glass and water. So glass refractive index is 1.5, refractive index of water is 1.4. So for which case the shift will be more? So if you see, if this is more, then this terms becomes less. So 1 minus less will be more. So if this is glass, this is more, so this will be more. Okay, now y, since it depends on refractive index, it also depends on as we talked about in the last lesson, refractive index is inversely proportional to the wavelength square. Okay, so if refractive index is less, wavelength is more, or if wavelength is more, refractive index is less, and so on. So this apparent shift depends on 3 parameters. One will be H, how much the denser medium is extended. Second is refractive index, and third is going to be wavelength. Okay, since refractive index and these are related. Now the second case, we are going to, in this case the medium was present in the, the object was present in the second medium, and we were looking from the first medium. Now suppose something is here, some object, and we are looking from inside the water, or you can imagine that suppose you are in swimming pool, you are looking at something outside. This may be bulb, bird, or anything. So what happens in this case? Suppose we take a incident ray like this, it goes straight, and if we take a incident ray at an oblique angle, then it bends towards the normal, so it goes like this. Now if I extend the refracted ray, you can see the image or the object will appear here. I am writing O prime. Now this is the real depth, then this is the apparent depth. So it means that suppose if you are inside the swimming pool and you are looking at something, it will appear to be raised up. Okay, and this case apparent shift you can see will be H prime minus H, and in this case H prime will be approximately N times H. Means here H prime is more than H. Okay, this question has been asked in 2020 board exam, that if the object is in rarer medium and you are looking from the denser medium, again these two rays looks very far apart, but they will be intercepted by your eyes. Okay, this relation is not important, but the ray diagram for this you guys should know. Again, if you talk about angle of incidence and so on, so this will be angle of incidence and this is angle of refraction. Now, next thing we are going to talk about is bending of a stick in water. Okay, bending the stick is just a thing, it can be pencil, pen, anything. So if you consider the first experiment we discussed, if you look from the top, you will find at the surface the pencil appear to be tilted or it's appear to be bent, but you have to look from the top, okay, not sideways I am talking about. So you will see that at the surface it appears to be tilted. Fine. So that we are going to talk about. So suppose there is water or any liquid, and suppose this is our stick which is immersed in the water. Now we'll take two rays. Let us take one ray here and let us take one ray here. Now you know that it will bend away from the thing and this will also bend away from the normal. Now if you extend these two rays, it is found that they will meet here. So what happens that this pencil is like this, and just now we talked about apparent shift. If anything is here, then it will appear to be shifted up. So because of that, this part of the pencil, it's appear to be shifted up, and this is called bending of the stick. Now generally they ask this question in board exam, they have asked it many times, and it carries 2 or 3 marks. And again, these two rays seems very far apart, but they are very close and they will be intercepted by your eyes. Right. Now we are going to talk about third application, is refraction through a glass slab. I discussed this question in the last lecture also, but let us just have a look. So suppose this experiment you guys will do in your class 10 practicals. So suppose there is a glass slab, and suppose there is a pin or anything here, an object is here, and we take one ray like this. This is the normal, and then it bends towards the normal, and then it bends away from the normal. Now this is the original thing. Now this distance is called lateral shift. Okay, the distance between this is called emergent ray. This is incident ray. So actually, if you look from this side, this pencil, see, your eyes cannot see the bending of the ray. Okay, means it will always see the rays to be coming in a straight line. You can't see the bending of ray until there is a change in medium and so on, but you can't see the bending of the ray. So actually what happens, even this thing is here, your eye will receive this, you will see the object somewhere here. Okay, it will be shifted. if you see from here, you will see this emergent ray. Now if I extend this, it will meet here, right? Huh? So actually you will see the pin will be laterally shifted to this point. Okay, this is called lateral shift. Now if I put the angles, and we talked about it, suppose this is the surface X, this is the surface Y, and this is the angle of incidence I, and this is angle of emergence E, and this is angle of refraction R, and this is also R, alternating interior angle. If you apply Snell's law here, you will find that I will be equal to E. Okay, please see the last lecture. So if you apply Snell's law on the surface X and then you apply Snell's law at the surface Y, you will find I is equal to E. That means that the emergent ray is parallel to the incident ray. Okay, and this is called lateral shift. Okay, that perpendicular distance between emergent ray and the incident ray is called lateral shift. So now this lateral shift will depend on 3 parameters. It will depend on how much is the thickness. Let us say thickness is T. So this lateral shift will depend on thickness of the material. More is the thickness, it will depend on angle of incidence, and it will depend on refractive index, and if anything depends on refractive index, it will obviously depend on the wavelength of the light used. Okay, now refraction through a glass slab, you can see the last lecture and you can find it out how to prove this I equal to E. Now the fourth thing we are going to discuss is experimental verification of laws of refraction. This is there in your syllabus. So fourth thing we are going to discuss is experimental as the name suggests, it should be carried in a lab actually, but it's there in your theory part also. So it's very simple. So we know we have 2 laws of refraction. One is Snell's law, and incident ray, refracted ray and perpendicular, they all lie in the same plane. So how to proceed in this experiment? You will take a glass slab and you will fix 2 pins like this. So this is your incident ray. So this is one pin, this is another pin. So this is my incident ray. You will draw a normal here, and then the angle of refraction. Okay, looking from this side, you guys can draw this. As I told you, this experiment is there in your class, so you guys will do it later on. Now these are 2 pins. Now this is angle of incidence, this is angle of refraction. So okay, so how actually we do? We see from this side, we put 2 pins here and put circle around it, and we draw incident ray, and looking from this side, we'll see where this pin is appearing, and there we'll put 2 pins. Okay, looking from this side, and then we'll complete this ray diagram, right? Now in this case, what we have to do, we'll draw a perpendicular from here let us say this is I, so this is, let us say, A, B, and we'll draw a perpendicular from here, and let us say this is CD, and we'll draw two perpendicular here. Now, so AB and CD are perpendiculars. Now, what we can do, we can find, let us say this point is X. So we can see the triangle ABX. So in triangle ABX, we can find sin I. Sin is perpendicular by hypotenuse, so perpendicular is AB in this triangle, and hypotenuse is BX. Same way in triangle CDX, we'll find sin R, and sin R will be CD by hypotenuse dx. Now, just imagine that we draw a circle here. Okay, of course it doesn't look like a circle, but let us say, keeping this constant, this point constant, we draw a circle. Then we can see that dx will be equal to bx because they are radius. So sin I by sin R. Okay, so if I draw a circle by keeping this point as a center, we'll find that this is the radius and this is the radius. So sin I by sin R will become equal to AB by CD. Now, according to Snell's law, sin I by sin R is equal to a constant called refractive index, right? So we'll make a table, and for different angle of incidence, so we'll change, in this experiment we'll change I, and if we change I, we know that AB and CD will also change for different I, and for different I we'll calculate sin I by sin R equal to AB by CD. So for each observation, so this is one observation, now we'll put suppose spin in a different way, so I will change, so AB will change. So we'll take different observation, and sin I by sin R will be equal to the length of the perpendiculars drawn from here, and through this we find that this sin I by sin R is equal to a constant. Okay, so this is the experimental demonstration or experimental verification for the laws of refraction. This is Snell's law. So for different I, we'll measure this ratio and it comes out to be constant. Now the first law doesn't need any verification. So it says that incident ray, refracted ray, normal, they lie in the same plane, and that is obvious from the diagram. Now this is the last topic I want to discuss, that is multiple images in thick plane mirror. So generally when we see mirror, it's thin mirror. Okay, we don't consider the thickness much, right? Now what happens, suppose you have a thick mirror. So let me draw the diagram. Suppose you have very thick mirror. Thick plane mirror. Now you can also imagine one glass slab is placed and we put a plane mirror here. Otherwise this is a very thick mirror. Now in this case, let us say one object is some bulb or a very small light is kept here. One object is here. Now suppose we are looking from this side. Now you can see this surface is transparent and this surface is polished. Now you all know that through transparent medium the light will go inside, and from polished surface the light will be reflected. Now suppose we take a light here, angle of incidence is 0, angle it goes like this and it will retrace its path, right? Because reflection will happen, but we need two rays to form the image. Now again you can sort of imagine, in case of plane mirror, if you object this, if you are here, then the image is formed along the same line. So we'll extend this line, right? Now let us say we take a light from here. Now mostly this is transparent medium, so most of the light will refract. So it goes inside. Then here most of the light will reflect. It goes like this. And then from here most of the light will refract and very little light will reflect. Now let me make this clear. Suppose this is 100% of light. So most of the light goes inside. So let us say this is 90%. Some part will be reflected. Let us say this is 10%. Okay, energy should be conserved. So 100 is 90 and 10. Now if you extend this, this is your first image. Okay, if I extend this light, so this is entering your eye, you will see the image. If you extend this here, now the first image is formed because of 10% of light. Now if you track down this 90%, since it is polished, most of the light will be reflected. So let us say 90% reflects. Now as it comes here, again this is transparent medium, most of the light will escape. Okay, refraction will take place. So let us say 85% goes out. So 5% is left. Now this light, if you extend it, this is image 2. Now image 1 is formed due to 10%, image 2 is formed at 85%. So second image is the brightest. Fine. If you track down now this also, then you will find that this third image is formed due to very less light. Okay, so this is the last topic. Let me know whether you guys followed this or not. Thank you.